Welcome back, everyone, to the second day of our workshop. Today, we're going to have two talks with a break in between, and then a short break and a discussion session. And it's a pleasure to introduce our first speaker of the day, which is Hans-Joachim Hein from Munster. And he will be telling us about the renormalized volume of a four-dimensional Ricci-flat ALE space.
Well, thank you very much for the introduction and for giving me the opportunity to speak here today. So my talk is going to have three parts. In the first part, I'd like to say a little bit about the general theory that motivated this work, and also the work in I think some of the other talks later this week. So in the second part, I'll talk a little bit more specifically about Kronehammer's gravitational instantons, which are still essentially the only examples of four-dimensional Ricci-flat ALE spaces that we know, at least that I know. And then in the third part, I will talk about this joint work with Olivier Bicard about the renormalized volume of a four-dimensional Ricci-flat ALE space. Okay. So let me start by writing down the big theorem in this area. So this is one of these convergence and compactness theorems in Riemannian geometry, and it's due to a combination of, I think, 6 people around 1990: Anderson, Bando, Shiger, Kazuo, Nakajima, and Tian. And it says the following. So suppose you have an infinite sequence of Einstein Riemannian four manifolds. And I want to assume that they're closed, so compact without boundary, and that they satisfy the following conditions. The first one is just a normalization of the Einstein constant. So Ricci of GI is lambda I GI, where the normalization is that I'm assuming that lambda I is at most 3 in absolute value. Then the diameter of all the manifolds along the sequence is supposed to be bounded above by some uniform constant d. The volume is supposed to be bounded below uniformly away from 0 by some uniform constant v. And the last condition is a little bit different. So I'm assuming that the Euler characteristics, so the topological Euler characteristics of the underlying four manifolds, are non-negative and uniformly bounded above by some constant g along the sequence. And well, so the last condition is actually just a substitute for something more geometric. So for four-dimensional Einstein manifolds, the Chern-Gauss-Bonnet formula tells me that, so for closed manifolds, the Euler characteristic can actually be computed as the integral of 1/8 pi squared times the square of the Riemann curvature tensor. So the fourth condition, so first of all, the Euler characteristic is always non-negative. So this is an observation that goes back, I think, at least to Berger. But what the fourth condition is really saying is that I'm assuming a uniform upper bound on sort of the curvature energy, the L2 norm of the curvature tensor of these metrics. And what the first three conditions imply, this is already almost the most important implication, is that if I look at geodesic balls centered at any point in any of the manifolds along my sequence, then it's at least as long as the radius is bounded above by 1 or by the diameter, then I know that the volume of this ball is sort of uniformly four-dimensional. The volume of a ball of radius r is bounded below by some uniform constant mu times the 4th power of the radius. So the manifolds look uniformly four-dimensional in a volume sense. And this is the main reason why we have some kind of compactness along the sequence, or the ability to prove some kind of convergence theorem. And the theorem states that under these assumptions, there always exists a subsequence that converges in the Gromof-Hausdorff sense some space M infinity G infinity, which is a priori just a metric space, a geodesic metric space. But in reality, it turns out, and this is the main content of the theorem, that this is actually a smooth, compact, four-dimensional Einstein orbifold. So not necessarily a manifold anymore, but at least an orbifold with finite singular set. So there's finitely many singular points that are modeled on flat cones over spherical space forms. And the convergence is actually smooth over the regular part. So away from these finitely many points in the limit space. So this is probably easiest to explain in a picture.
So hi, can I ask something?
Sure.
Is there any statement? I mean, in general, I guess there isn't uniqueness, but is there any statement which guarantees uniqueness in this of the limit?
I mean, you could always do something stupid, right? Like just take two sequences and mix them. I don't know how you figure out something like that.
Okay.
Yeah, I don't know. All right. So, well, I mean, but you know, what you typically have in mind is some sort of continuous one parameter family of manifolds that converges nicely, sort of in a reasonable way. And then it's more about sort of describing what the convergence actually looks like along this family. And I think this is the picture that everybody has in mind. So I have a mode of convergence that's usually called bubble tree convergence. So the black thing is the limit space. So it's my four-dimensional Einstein orbifold. So in this example, it's smooth except for one isolated singularity here at the black point. So singularity looks like the cone over S3 mod gamma for some finite group gamma. And then shortly before the limit, I have topology disappearing into the singularity. So that's the red and the blue parts. You know, just as an example, you could imagine that sort of the topology in the red part here has diameter proportional to 1 over I, where I is the family index. So this goes to 0. So the topology goes to a point, to the singular point in the Gromov-Hausdorff sense. And then, so this is one bubble that's forming, but then here I have a bubble forming on top of the bubble. So I have some more topology pinching off, but at a much smaller scale, let's say 1 over I squared. And then the idea is that if you take the red part first and rescale distances by a factor of I, so you rescale the metric tensor by I squared, then the topology is going to have unit size after rescaling. And this part here sort of looks conical, but gets blown up and becomes an infinite conical end. And this is what makes the metric asymptotically locally Euclidean, or ALE. So one subtlety here is that if I perform this rescaling and if I pass to the limit, then I don't necessarily get a smooth space. So after rescaling, the blue parts still have diameter 1 over I, roughly. So that's still a singularity forming. So this limit space is only going to be an orbifold itself. So it has an infinite ALE end, but there's also an orbifold, an isolated orbifold singularity in the interior, where sort of this blue topology has pinched off on an even smaller scale. But if I actually go to the scale of the deepest bubble, 1 over I squared, so if I blow up all distances by a factor of I squared, then I actually converge to an honest, smooth Ricci-flat manifold, which is again ALE. But now the cone at infinity is going to be sort of this blue cone here that you're beginning to see in the picture, and the red parts and the black parts of the manifold are just going to get sort of blown away to infinity, and then the limit of the blue part is actually a Ricci-flat ALE manifold without singularities. So the key points in the proof of this theorem was basically 3 points. The first one is Gromof's compactness theorem, which allows you to extract some subsequential limit which is some kind of metric space without any sort of obvious good properties. And then you want to do regularity theory on this limit space. And then the two main points are that, well, first of all, you have an epsilon regularity theorem, which says that if you have some ball with a small amount of L2 curvature, where this epsilon only depends on the sort of bounds that I fixed along the sequence in the setup of the theorem, then I actually get this kind of elliptic regularity estimate that allows me to bound the pointwise curvature on a smaller ball in terms of the average L2 curvature on a slightly larger ball. And the constant C is again uniform along the sequence. And then maybe really the single most important point is the last one, that I've been assuming that there's only a finite or a bounded amount of L2 curvature to go around along the sequence, and that the L2 norm of the curvature is scale invariant in dimension 4, right? So curvature is like 1 over distance squared. L2 curvature is like 1 over distance to the 4th times volume, which just goes like distance to the 4th, so it's a scale invariant. You know, if you look at these ingredients, then you see that, well, it's pretty clear that all of these ideas and the statement and the proof of this theorem were sort of modeled on the compactness theory for Yang-Mills instantons and maybe even harmonic maps that Karen Wullenbeck had developed a couple of years earlier. So in particular, this curvature energy, the L2 norm of the curvature, is of the analog of the Yang-Mills energy in this setting. So this was back in the early 90s or even in the late 80s. And what has happened since then is mainly that people have looked at sort of the higher dimensional versions of this convergence theory. And of course, the L2 norm of the curvature is no longer scale invariant. It's subcritical with respect to scaling. So it's not really clear what, if anything, this controls, what kind of control you can get from an L2 curvature bound, not to mention the fact that in general, for a general Einstein manifold in higher dimensions, you don't really have an a priori L2 curvature bound that comes from anything. You do have that in examples with special holonomy, but not for an Einstein manifold of generic holonomy. So this is one way in which dimension 4 is very special. So nevertheless, there's been sort of a huge amount of work, very technical work being done on these compactness questions for sequences of Einstein manifolds in higher dimensions. And to my mind, at least, sort of the pinnacle of this development was the result of Chigger and Neighbor in 2014, which states something vastly more powerful and more general, but specialized to our situation. So in particular, in dimension 4, it actually tells us something fundamentally new, which is the statement that the uniform bound on the Euler characteristics or on the L2 norms of the curvature in our setting, so if in the setting of the theorem that I wrote down on the first page, is automatically satisfied. So there exists an automatic a priori bound on this curvature energy that only depends on the other constants that I fixed along the sequence. So much for the general theory. What are the open questions? Let's only restrict to dimension 4. Well, open problems, it's always kind of a dangerous statement to make, and at least to my knowledge, those are open problems right now, today. So the first one is what I want to call the reconstruction problem. So this is about the converse question. You suppose you have all the building blocks, compact Einstein 4 orbifold, and the matching set of Ricci-flat ALE spaces, possibly with singularities. You can sort of try and stick them together. I mean, topologically, you can, assuming that the groups, the orbifold groups match up, so you can construct a smooth 4 manifold, at least topologically. Question: can I actually glue the Einstein metrics and perform some kind of gluing construction that gives me an Einstein metric or a family of Einstein metrics on the smooth 4 manifold? So one special case of this problem is Anderson's football conjecture. So maybe the simplest kind of Einstein four-orbifold that you can imagine is one that actually has constant sectional curvature. So the easiest thing would be to take the four-dimensional sphere and apply a finite group of rotations in the cross-section S3 in the equator, because of kind of football with two orbifold singularities at the poles. And Anderson conjectured that this kind of constant curvature orbifold can never be a Gromov-Hausdorff limit of smooth Einstein four manifolds. So in this case, this reconstruction problem would be really fundamentally obstructed. And I think we're going to be hearing much more about this in Tristan Ozush's talk in this workshop. I hope. Then maybe the other problem, the big open problem, is that we don't actually know a whole lot, or at least I don't know a whole lot about the classification of these bubbles. So what are the possible Ricci-flat ALE spaces in dimension 4? What examples do we have? So what could be the possible building blocks in a gluing construction like this? And well, so the only ones known to me are the ones that have reduced holonomy equal to SU2. So it's the hyperkähler examples of Kronheimer. And well, so the work that I want to talk about today has maybe some very modest bearing on both of these problems. But again, I think we're going to be hearing much more about this in Tristan's talk. So today I just want to explain what we actually proved. And for this, it's helpful to recall the definition, constructional properties of Kronheimer's gravitational instantons. Just it's good to have as background knowledge, but also there's one aspect that's going to be directly relevant to what.
Could I ask one?
Sure.
Just so under some spin assumptions, then there are some results saying you
Sure.
have to have that, but those are still very, very restrictive.
Right. So this is an observation that goes back to Nakajima, as far as I know, to sort of the same body of work that I mentioned in the beginning, that you can actually use Witten's proof of the positive mass theorem to show that if the manifold is spin, so if you can use the method of harmonic spinners, then the hyperkähler or locally hyperkähler examples are the only ones. But I mean, that depends on how you want to look at this. I would tend to say that this is a very restrictive assumption. So yeah. Certainly the open problem, to my knowledge, is to say anything at all about the non-spin case, or cases that are sort of closely related to the spin case. Okay. All right. So let's take a look at the gravitational instantons of Kronheimer. So by definition, a Kronheimer gravitational instanton is a complete ALE Riemannian four manifold, which is simply connected and whose holonomy group is equal to SU2. So in other words, the metric is Calabi-Yau with respect to some parallel complex structure. In dimension 4, it's actually equivalent to saying that the metric is hyperkähler. So you actually have a whole S2's worth of parallel complex structures. And this by itself already implies that the metric is necessarily Ricci-flat. And again, up to taking finite quotients are the only examples of four-dimensional Ricci-flat ALE spaces known to me.
Oh, can I ask a question about that last point, taking finite quotients? Are there any examples of smooth finite quotients of any of the Kronheimer, ADE examples?
There are, and they've been classified. And it turns out that they all preserve at least one of the parallel complex structures, where they're all actually Kähler, and not just locally Kähler.
Is there a reference for that?
Sure, I can send you a reference after the talk, maybe. I mean, the classification is not particularly nice. It's not something that you could state easily.
Okay, thanks.
Okay, so let me try and describe what the what the Cronheimer spaces themselves actually look like, at least roughly, or how you might go about constructing them. And this is sort of a slightly biased description. This is not exactly how Cronheimer thought about this, wrote about this in his papers. Although, I mean, in spirit, it's really close enough. So the only difference is that I want to describe the construction in terms that don't explicitly use the hyperkähler structure and that don't explicitly use any twistor theory, so that there's actually a nice way of proving an analogous result for higher dimensional Calabi-Yau manifolds. So what are the ingredients? So how much? Okay, yeah, that's basically it. You start with a finite subgroup of SU2 that acts freely on the 3-sphere, and you take the quotient of the trivial Calabi-Yau structure on Euclidean space C2. So I'm taking the trivial flat Kähler structure Gj and the trivial parallel holomorphic volume form or symplectic form capital omega. Take the quotient by gamma, and this would be an example of a Calabi-Yau cone. And in complex dimension 2, these are the only examples of Calabi-Yau cones, quotients of C2 by finite subgroups of SU2 acting freely on S3. Then it turns out that Calabi-Yau cones are always affine algebraic varieties, and in a two-dimensional case, this is very classical. So this goes back to work of Felix Klein in the 1800s. That, in this case, is basically the invariant theory, the theory of polynomial invariance of these finite groups. So I'm always able to embed these cones as quasi-homogeneous affine algebraic varieties. So in this case, affine algebraic surfaces into C3 even. And then what I can do is, once I have an embedding like this, I can deform it C-star equivariantly, where the C-star action in this case is just given by the scaling vector field on the cone by the vector field r times d by dr. So I look at one parameter C-star equivariant deformations where infinity in the cone is held fixed. So there's some non-trivial topology, some vanishing cycles being created near the origin, near the vertex of the cone, and this is going to be sucked into the vertex of the cone by the C-star action. So if after I perform this deformation, it could still be that my affine surface has some residual singularity. So there could be remaining singularities, which would necessarily have to be isolated quotient singularities of the same form as the one I started with, except that the group could be different. So the group could be smaller. And then finally, I can perform Krepin resolutions of these singularities, which creates holomorphic spheres, rational curves of self-intersection -2. And then to get my Ricci-flat metrics, my Ricci-flat Kähler metrics, so that's the point of view that I like, is that, in each class, in each Kähler class on a Krepin resolution like this, you solve a complex Monge-Ampere equation with sort of Dirichlet boundary data at infinity, so that your metric is going to be asymptotic to a flat cone metric. And what characterizes the Kähler classes among arbitrary 1-1 classes on a resolution like this is that they have to pair positively with the exceptional curves. So the pairing with all the -2 curves has to be strictly positive. And that's finitely many, at most finitely many linear inequalities that a class needs to satisfy in order to be a Kähler class. And so then you get this picture that the Kähler cone, a cone of Kähler classes of Ricci-flat Calabi-Yau Kähler metrics on these manifolds has at most sort of finitely many linear boundary pieces. So it's bounded by at most finitely many hyperplanes. And each of these steps is essentially reversible. So this is a construction but it turns out that even in a more general setting in higher dimensions, so these are sort of the only degrees of freedom that you have for a construction like this, and this is why you get a classification at the end of the day. Well, Kronheimer's original point of view was slightly different, so he was more focused on the hyperkähler structure, and in particular, he phrased the classification in terms of the period vector or the period point of the hyperkähler structure. So I emphasize the complex structure and the Calabi-Yau structure a little bit more, but of course, in the hyperkähler case, they're interchangeable to some degree. So the period point zeta, this would be a triple of cohomology classes, the cohomology class of the Kähler form and of the real and imaginary parts of the holomorphic volume form or holomorphic symplectic form. In H2 of the underlying manifold, H2 is identified with H2C naturally, so the natural map is an isomorphism in this case. So this is the space where the period point lives, and of course I can mod out by the action of SO3 by hyperkähler rotations. So then I get this cohomological period vector, and one way of phrasing Kronheimer's theorem would be to say that this vector uniquely determines an ALE hyperkähler metric on this underlying smooth 4 manifold. So the reason I mention the period vector is that this is going to play sort of a very explicit role in the story that I want to tell today. And so to my knowledge, the only written reference for this is in the PhD thesis of Hugo Vray in 2013. And what he did is that he actually explicitly computed the leading terms of the asymptotic expansion of the Kronheimer hyperkähler metrics. So the leading term is of course Euclidean, but then you look at sort of the first sub-leading or sub-Euclidean term that decays like distance to the -4. And well, so he computed these terms explicitly in terms of the period vector zeta. Turns out that this is possible. And this is sort of the formula that set everything in motion that I want to talk about today. And sort of briefly, the idea is that what Kronheimer showed in his papers is that you can take your ALE space M4 and remove a finite union of compact two-dimensional surfaces, sigma 2, with a finite CW complex if you want. If you do that, then M becomes, so the complement becomes diffeomorphic to the complement of the origin in the asymptotic cone, in the tangent cone at infinity. And you can choose this diffeomorphism in such a way that two conditions are satisfied. First of all, this is actually an ALE coordinate system for the Kronheimer ALE hyperkähler metric. So I have convergence in these coordinates to the Euclidean metric up to errors that fall off like distance to the -4. And what's more, so because there's a hyperkähler quotient construction lurking in the background, I have the Archimedes property that if I push forward the hyperkähler volume form under this diffeomorphism, then it's going to be identically equal to the Euclidean volume form on the cone. And then using these two properties, it is possible, and this is what Vray did, to calculate the leading terms of the metric explicitly in terms of the period vector. And basically what you do is, well, you have a hyperkähler structure, so you have three parallel Kähler forms, and then you can use Hodge theory on ALE spaces as in Dominic's book, to write them in terms of harmonic representatives, L2 harmonic representatives, which are directly related to these cohomology classes and compactly supported cohomology. So that's your direct connection with a period point. And then you just write down the hyperkähler conditions, which are saying that, the pairwise wedge products of sort of the intersection matrix of the hypercalar triple, I should really say the pairwise wedge products of the three calar forms, give you multiple of the constant multiple of the identity, and then you integrate this by parts over larger and larger balls, and you make an asymptotic expansion of the boundary terms when you integrate by parts. And it's a horrendous computation, but it actually gives you a solvable system for the leading order terms of the metric. And at one point, you crucially use this volume normalization condition star, the green condition, at least that this is true to leading order at infinity, but that's already a non-trivial statement. And in this way, you can get an explicit formula for the leading terms of the metric in terms of the period vector.
Can I ask a question in between?
Sure.
So you're talking about the leading terms.
Yes.
Does it mean like you get not only the r⁻⁴ term, but also other like faster decaying terms, or is it just about the r⁻⁴?
It only picks up the r⁻⁴ terms, unfortunately.
Okay, I see. Thanks.
There's not a lot that's known, I don't think, about the higher order terms. And so, okay, so one of the key observations which started all of this, so the work that I want to talk about, is that, well, if you look at Auvrais' formulas, there's sort of one canonical direction in the space of possible r⁻⁴ tensors, which is the Hessian of the Green's function on Euclidean space. So this is one of the first candidate term that you would normally think of in an expansion like this, has all the formal properties that you need. So 1/r² is a harmonic function on R4. Take the Euclidean Hessian, you get a symmetric 2 tensor. So a deformation of the flat metric as a Riemannian metric, and indeed as a Ricci-flat Riemannian metric. And the component of these Auvrais terms in the direction of this most canonical term is exactly -1/6 times the norm squared of the period vector zeta. And this is very suggestive. So you have a sign there, and that's should always be happy when you get a sign. And moreover, you have a rigidity theorem. So this component vanishes if and only if the period vector is 0, which by Kronheimer's Torelli theorem happens if and only if the ALE space is actually isometric to the flat cone. And then, well, sort of, what we do in the proof of the theorem is to, well, first of all, interpret this number as a renormalized volume, so to find some sort of Riemannian geometric interpretation of this number, and then show that you have the same comparison theorem, so the same inequality, that this renormalized volume is always less or equal than 0, together with a rigidity statement that it vanishes if and only if the manifold is actually isometric to its asymptotic cone. But the point is that we prove this on all Ricci-flat ALE spaces. If it so happens that Kronheimer's examples and their finite quotients are the only ones, then the statement would be a corollary of this computation in Auvrais' thesis. But the point is that we found an argument that proves an analogous inequality, or once you understand this inequality in the right way, intrinsically, to prove this on an arbitrary Ricci-flat ALE space. And this is what I want to describe in the rest of the talk. Okay, so here's the setup. Let's say M4G is a Ricci-flat ALE space, not necessarily hypercalar or locally hypercalar. Interesting cases when the holonomy would be SO4, so the generic holonomy case. And then if you want this can be the definition of an ALE space for you. So I didn't write it down very precisely. But basically you have, well, a compact part that contains all the non-trivial topology K, and then you have a diffeomorphism from M minus K to, well, if you want the punctured flat cone, or you could have removed a compact set unit ball around the origin in R4. But the point is that under this diffeomorphism, I want to assume that, so if I push forward the Ricci-flat ALE metric and subtract the Euclidean metric, and if I call this tensor H, then this goes to 0 with respect to the Euclidean metric as the radius goes to infinity. along with all derivatives if you want. You can assume that you have an improvement at each time you take a derivative. You gain a factor of 1 over r, something like that, up to some sufficiently high finite order. Okay. So then one standard move in this business is that you impose a gauge fixing condition. And the well-established gauge fixing condition, if you're dealing with Einstein metrics, it's probably the only reasonable one, is the Bianchi gauge fixing condition, which is that you say that it's possible to adjust your diffeomorphism phi so that while the ALE condition on the metric is satisfied, it still converges to the Euclidean metric. But in addition, this tensor H, the difference, is in Bianchi gauge. So the Bianchi operator is 0, the Bianchi operator with respect to the Euclidean metric. Where in general, if you have a metric G and a symmetric 2 tensor H, the definition of the Bianchi operator is this. So Bianchi G of H is a 1 form, the divergence of H minus 1/2 times the gradient of the trace of H. And you have this useful Bochner formula that if you apply Bianchi to the Lie derivative of the metric by a vector field, you get minus the Laplacian of the vector field, the rough Laplacian of the vector field, plus the Ricci curvature applied to the vector field, which is the same Bochner formula that you would use to prove that compact manifolds with negative Ricci curvature don't have any non-trivial killing vector fields. It's exactly the same formula. And what this formula suggests is that the Bianchi gauge fixing condition is actually a useful condition, because, I mean, what does gauge fixing mean? You want to change your metric by a diffeomorphism at infinity. So infinitesimally, you want to change the metric by a term of the form Lxg, where x is a vector field that's to be determined, so that this whole Bianchi thing is 0 in the end, where it corrects the Bianchi of the original tensor to become 0 after the gauge fixing. And then you see if you're already Ricci-flat, then all you have to do is invert the rough Laplacian on vector fields outside a compact set. And this is certainly, this is fairly easy to do on an ALE space. It's just basically just inverting the Laplacian on scalar functions away from a compact set in Rn and R4 in this case. So this is a useful gauge fixing condition. And it turns out by this sort of argument that you can always achieve that, well, just some kind of, I'm going to write, I wrote down 3 statements here, and they're coupled together. But what you can achieve using this gauge fixing technique is, well, these 3 properties, that H can be written as H naught plus higher order terms, where H naught is a leading term. H naught sees the Bianchi gauge fixing condition, so it is in Bianchi gauge with respect to the Euclidean metric itself. And then what you get, so the Einstein equation, the Ricci-flat equation, becomes elliptic in this gauge. What you get from this is that the leading term is actually a harmonic tensor on R4 minus a compact set. So the Euclidean Laplacian is 0. So that's 3 statements, including the fact that these terms are of higher order in some sense, that you prove simultaneously. It's not the one after the other, but it's sort of a manifestation of the fact that the Einstein equation becomes elliptic in the right gauge. And then you say, well, if this is a harmonic tensor on R4 minus a compact set, then this means that the component functions, if I pass to the universal cover, so if I remove the action of this finite group, the component functions are harmonic functions. And then, well, you know what the harmonic functions on R4 minus a compact set look like. Well, the first possibility is the Green's function, but then it turns out that tensors that are proportional to the Green's function are ruled out by the gauge fixing condition already. So that's a fun little computation that you can do if you take 1 over R squared times a constant matrix that's certainly harmonic. If it's in Bianchi gauge, then you see it has to be 0. There's no other choice. Then the next possibility is linear polynomials, homogeneous linear polynomials divided by r to the 4th. So those are terms that decay like 1 over r cubed. It turns out you can't have those because you're imposing symmetry invariance under this finite group, which is not trivial. So that knocks out the next term in the expansion. So the only term in the expansion that you can actually see is the 1 over r to the 4th term, so quadratic polynomial, divided by radius to the 6th. And that's the terms that you actually see in the Kronheimer examples. So this is the asymptotic structure of a general Ricci-flat ALE space, and this is how you get it by imposing a Bianchi gauge condition.
Sorry, when in do all quadratic things appear as possible asymptotics of Kronheimer things, or there are some that would not be?
Yeah, this is sort of going to be the main
Okay.
point.
All right. Sorry.
Last theorem state. I mean, already the Bianchi gauge condition rules out some, because any tensor of this form, quadratic over r to the 6th, would be harmonic. But not every harmonic tensor actually satisfies the Bianchi gauge condition. So this is a property that you already use to rule out the 1 over r squared terms. Okay. So here's another idea that's been around for a long time. That was another source of motivation for the theorem that we ended up proving, that on the asymptotic cone R4 mod gamma with a Euclidean metric, you have certain special vector fields, associated to dilations and isometries. If the vector field x naught, which is just a scaling vector field, r times d by dr, that's a conformal killing vector field. And then you have infinitesimal rotations, so elements of the Lie algebra SO4 that are invariant under your finite group. That's the killing vector fields of the asymptotic cone. And as a small side remark here, that I want to note that if you're, this is everybody's favorite case, if your finite group is Z2, so for example, what you see in the smallest possible non-trivial group, which is what you see in the Ricci-Hansen metric, then the space of invariant elements of SO4 is just all of SO4. So of course, if you're just sending, if your only non-trivial group element is minus the identity, that's going to preserve every linear vector field, so in particular every infinitesimal isometry of the flat metric. Rotational isometry, you have to fix the origin. Another question that's been around for a long time is, how about we try to take these special vector fields on the asymptotic cone and extend them to conformal killing vector fields or killing vector fields on the Ricci-flat ALE space. So find an X on M4G such that under this given diffeomorphism, X is asymptotic to X naught, so the difference is of lower order, grows sublinearly at infinity, and such that this X is actually a killing vector field or conformal killing vector field with respect to the Ricci-flat metric. Of course, that's a question that you can answer immediately. Of course not. Can't find such an X in general. There have to be obstructions. So the nicest picture perhaps is in the case of killing fields. So in the second case, so if you're trying to extend an asymptotic isometry to a global isometry of the Ricci-flat metric. So for example, if you look at the Ricci-Hansen metric, where the group would be Z2, the group at infinity, so then every element of the Lie algebra SO4 actually pushes down to the asymptotic cone. Well, but we know the isometry group of the Iguchi-Hansen metric, and at least it's the connected component of the identity, is U2. It's not SO4. So there are two directions that are missing. So certainly not every element of SO4 extends to a killing vector field on Iguchi-Hansen. And well, in the conformal killing case, the answer is a little bit more indirect, but it's also more general. So if you assume that you found a conformal killing vector field on your Ricci-flat ALE space that's asymptotic to the scaling vector field on R4 mod gamma, and if in addition you assume that it's a harmonic vector field, which is a very mild assumption if you already assume that you're conformally killing, so it's something that can be satisfied after some change of gauge, then it follows that, well, the divergence of the vector field has to be constant. So X does not just generate infinitesimal conformal transformations, but actually infinitesimal dilations. And then it's kind of clear that if you have a dilation symmetry, then the manifold has to be flat because it's asymptotically flat. So it cannot have any non-trivial curvature. This means the manifold has to be isometric to its asymptotic cone. So you literally never have this conformal killing extension except in the trivial case where your manifold is isometric to its asymptotic cone. I shouldn't say manifold, it's only an orbifold really in this case, but that doesn't make a difference to anything that I'm talking about. Well, so that goes in the right direction. So this goes in the direction of this rigidity theorem that I'm aiming for. And basically all that we do is that in the paper is that we calculate the obstructions to extending RDR to a global conformal killing vector field on the Ricci-flat ALE space, and we interpret them geometrically, and turns out there is a nice natural interpretation in terms of the renormalized volume. And that exactly gives us the sign, this -1/6 times norm squared of zeta that we had from the explicit formula of the leading term of the metric in the Kronheimer examples. But it works in general without assuming that the metric is hyperscalar. And maybe I'll just go through the steps of the proof. So once you have the right idea, the proof is not particularly difficult. So basically you just do computations all the time. First, you construct a harmonic function on the manifold whose Laplacian is identically, not harmonic, the Laplacian is identically equal to 8. And asymptotically, the function is equal to r squared under this asymptotic coordinate system phi. And then it turns out that you can get a refined asymptotic expansion for this function. So assuming that you have a Bianchi gauge and assuming in addition that the leading term of the metric is trace-free with respect to the Euclidean metric, you can prove a refined expansion, which says that in these coordinates, this function whose Laplacian is equal to 8 looks like r squared. Well, you could always add or subtract a constant, so let me ignore this. But then the next term is a constant multiple of the Green's function on R4, and then you have higher order terms. So this is a fairly standard thing to do in analysis on asymptotically flat manifolds. But the important point is that under these two conditions here, one of which we already satisfied, with the next condition is new, then it's true that I have this refined expansion of the solution. And the solution is unique.
So which things are 4-dimensional specific and which things would have a higher dimensional? I mean, obviously the precise powers and things, but
that's a good question. I didn't actually think about that. So I think I'll have to get back to you on that.
okay. I mean, obviously you don't really have many hyperscalar ALE, but
or any examples for that matter in higher dimensions. I mean, but you know, it's a good question. I didn't embarrassed to say I didn't actually think about it. But it should be fairly easy to work out.
yeah, I mean, at least some of the things that you were doing seem like they might
Yeah, definitely. But so we'll get to the part that's specifically four-dimensional in the end, and this is the answer to your other question. But I'll do a couple more steps that are still fairly general. So your obvious candidate for a conformal killing vector field, even harmonic conformal killing vector field, would be the gradient of this function. And then the Bochner formula tells me, well, it does tell me that this vector field is harmonic. So gradient of the Laplacian is 0 by construction. But then what I actually want to do with this is I want to say that, well, the Laplacian of the gradient of a function is, that's by definition the same thing as minus the divergence of the Hessian. And then I can take out the trace part of the Hessian because the Laplacian is constant. So the divergence kills that. So this is the same as minus the divergence of the trace-free Hessian. And then I can just integrate this against the gradient of u and integrate by parts. And then obviously on the left-hand side, the volume term is going to be the norm squared, the L2 norm squared of the trace-free Hessian. And this is going to be equal to some boundary term. And I want to integrate this over a domain omega r, where omega r is a region in the manifold, while the region that's interior to the coordinate sphere at height r. So I'm using my given diffeomorphism to map the Euclidean coordinate sphere to the ALE space, and then I'm looking at the domain interior to this. And then, of course, you want to calculate the asymptotic boundary term. And what you get is that, well, it's equal to 12b plus terms that goes to 0, that go to 0 where b is exactly sort of this nice Green's function term from the asymptotic expansion of this special function. There's a caveat here that in the computation, you also use the property that h naught of dr is 0, where h naught is again the leading term of the Ricci-flat metric, and r is just the radial unit vector field in R4 or R4 mod gamma. So if you do have that, then this boundary integral simplifies this very nice way into leading order. You just get this, this constant. So the upshot is that this constant has a sign, and it's 0 if and only if, well, the trace-free Hessian of u is 0, meaning that this function, the gradient of this function u, is actually a conformal killing vector field. And at this point, you can forget about the motivation with conformal killing vector fields or killing vector fields. So in this case, I mean, this is just a statement. Geometric analysis about properties of the special function u. And now I want to interpret that geometrically. That's the third step. Well, and what's the only thing left to play with? Well, the Laplacian of u is 8, so you integrate that over this domain omega r. So you get that 8 times the volume is equal to a boundary term. And then, well, the boundary term, you can do an asymptotic expansion, and it gives you 8 times the volume in Euclidean space. That's not surprising. What's maybe slightly surprising is that the next term is, again, very clean. You just get minus b, plus terms that go to 0 as r goes to infinity. So we have this constant b. That's the obstruction to creating a conformal killing vector field on the ALE space, if you want to think about it that way. But now it actually shows up as the leading term in the comparison of the two volumes, this domain omega r and the Euclidean ball of radius r. And again, in this asymptotic expansion, to have the computation come out in this relatively clean way, what you have to use is the 3 conditions, again, that I already wrote down. The Bianchi-Gage condition on the leading term, the fact that it's trace-free, and the fact that its contraction with the radial vector field is 0. Okay. So summary. If the 3 conditions, the red conditions, are satisfied, then this volume difference has a finite limit. As the radius goes to infinity, the limit is non-positive and it vanishes if and only if the manifold is isometric to a flat cone, to its own asymptotic cone. Questions. So what's the deal with the three conditions on H0 that I wrote down? First of all, what do they mean geometrically? And second, can we always satisfy them? Because otherwise that would not be a very interesting theorem. So the meaning of the three conditions is easily explained. What they imply is that, well, the boundary of this domain, which by definition is just the image of the coordinate sphere of radius r under this ALE coordinate system, is actually CMC to one higher order than expected. Of course, you would think that these coordinate spheres are asymptotically of constant mean curvature because that's true in Euclidean space. That's not an interesting statement. But the expected rate of the relative error, the relative deviation of the mean curvature from being constant, is 1/r⁴. And now it turns out that under the three conditions, it follows that it's actually 1/r⁵, one higher order than expected. And what this means is that, well, on asymptotically flat manifolds like this, you have a canonical CMC foliation that's very easy to construct and to prove to be unique in this case because the group at infinity is non-trivial. So you don't see any of the difficulties of Husk and Yau in this case. So you have this canonical foliation of the end by constant mean curvature hypersurfaces, and because omega r is such a good approximation, or the boundary of omega r is such a good approximation to this foliation, you can just replace boundary of omega r by the leaves of this foliation throughout the whole computation, and you're just going to incur negligible errors. So this domain omega r that we're integrating over actually has a natural canonical geometric meaning. So that's intrinsic to the manifold, intrinsic to the geometry, even though a priori I defined it in terms of properties of this coordinate system. Well, and the second question is, can we always find a coordinate system phi that satisfies, so that the leading term of the Ricci-flat metric does satisfy the three magic properties? And well, in some sense, this is maybe the main theorem of the paper. Well, you can. If you look at the space of all possible leading order terms of the Ricci-flat metric, so this is all the symmetric 0,2 tensors H0 on R4 minus the origin that are in Bianchi gauge with respect to the Euclidean metric. That's one of our three magic conditions anyway, which are also harmonic, meaning that each component function is a harmonic function. And then more specifically, I want to assume that each component is homogeneous of degree -4. That's the relevant case for leading terms. I'm sure if you're better at representation theory than we are, you could prove that this is 26 dimensional, but we did that by computer calculation. So you have to find enough subspaces to make up 26. There's one subspace that's relatively obvious. That's all the Lie derivatives of the Euclidean metric. It should have been the Euclidean metric here. With respect to harmonic vector fields of decay rate r⁻⁻3. So linear functions over r⁴ times coordinate vector field. So the coefficients Lij are just an arbitrary 4x4 matrix. That's sort of the residual gauge freedom that you have in this space. That's 16 dimensional as r⁴ times 4. And so those are harmonic tensors that do satisfy the gauge fixing condition, the Bianchi condition, but they're still pure gauge terms, so you can eliminate them by adjusting the diffeomorphism phi, the ALE coordinate system. So you only have to worry about what's left. And lo and behold, well, the Kronheimer tensors have to be in there, the leading terms of Kronheimer spaces. And their images under orientation reversing reflections of R4. So that's a 10-dimensional space. So 10 equals 5 plus 5. As a representation of SO4, it's the half spinor representation S4 plus and its image under reflections. And then you can just check by going through these terms. So this happens to be the same representation in which the Weil tensor of a Riemannian metric in 4-dimension transforms, the symmetric, the trace-free symmetric 3x3 matrices. And you can just check by inspection, so by brute force computation, that all of these terms, which we know explicitly from Auvre's thesis, actually do satisfy the remaining conditions that we need, which is that they're trace-free with respect to the Euclidean metric. And actually, that if I contract them with a radial vector field in one variable in one slot, I get 0. That's true by inspection. That gives me 16 dimensions. There's only 26 in total, and this tells me that this gauge fixing, these three conditions that make the theorem hold, can always be satisfied by gauge fixing, because to leading order, any Ricci-flat ALE space at the end of the day looks like a Kronheimer plus the image of a Kronheimer under reflection. That's the content of this theorem. Okay, that's it. Thanks very much for listening.
Thank you very much, Hayo. Let's thank Hayo for this very clear presentation. And we can take questions or comments.
In this last slide, do you need to look at the gamma invariant part of these tensors? I know a bit.
That would presumably simplify things a little, especially if gamma is big, but we don't actually need the group gamma. So this is really just a property of harmonic tensors on R4.
Right.
I would have a question.
Yeah, please go ahead.
So what is so specific at 4 dimensions?
Also this theorem. We didn't
Okay.
even bother to try and see what happens in higher dimensions.
What about other asymptotics like ELF or ALG? Could you?
I mean, that would definitely change a lot of the powers of the radius function that occur throughout. You could certainly try. We haven't tried.
Okay, thanks.
No obvious answer, and it could be interesting.
So, I mean, the most obvious thing is you're missing the 10-dimensional Kronheimer thing in higher dimension. Yeah.
Right. But I mean, this was really just a way for us to simplify the work. So, we can. I mean, this right here in the first line is the relevant space of tensors. You can just calculate what that looks like using representation theory or by computer. And then it just turned out that we already knew everybody in that space. We happen to know the leading terms of the Kronheimer metrics, but in principle, you could just calculate the space explicitly in all dimensions or in other asymptotic geometries, and then check that all the elements in the space do satisfy all the properties that you need for your proof to go through. So this is more like, we saw that it worked in 4 dimensions with ALE geometry. Really happy about that.
I mean, I guess following up on Simon's question, I mean, if you don't even know, if you have generic holonomy and then your gamma could be some other subgroup of SO4 and not a
Right.
SU2, then maybe you are interested in knowing something more about further restrictions from having gamma in SU2 and the gamma invariant pieces.
I mean, that could conceivably help you in higher dimensions if somehow the exact aspect of the theorem wasn't true. then certainly somehow knowing something about these groups could help.
Right, thanks.
But in dimension 4, I mean, we do know all of them. It just turns out we don't need to know anything about them because the theory is already true without sort of considering the groups.
Yeah.
Are there any other comments or questions? If not, let's thank Hayo again